Question 7. In this question, we are interested to determine the ratio upthrust on ice when fully submerged to upthrust on ice when it is floating. So take note that there are actually two situations. The first situation is when ice is held below the surface of water, and second situation when it is floating at the surface. So let's look at the first situation. The first situation is when it is held below the surface of water. So let me write the forces acting on it. First, you have the upthrust, I call it U1, and then you have the weight of ice. And then in order for it to be below the surface of water, there must be an external force holding the ice. So actually, for equilibrium to take place, the upward force U1 must be equal to the sum of downward forces F external plus weight of ice. According to Archimedes' principle, the upthrust U1 is equal to the weight of water displaced. So I'll write mWg, right? So I also know that density of water can be written as mass of water divided by volume. So now I can have mass as density of water times volume, giving me the mass mW. So this mW times G, which is U1, this one gives me the relationship between upthrust, density of water, volume of the ice block. Right. We move on to the second situation. Second situation, the ice floats on water. So let me write the forces acting on the ice block. We have upthrust U2 and the weight of ice, right? So this time there's no external agent holding it. So it's just upward force equal to the downward force. So I write the second equation, U2 equals to weight of ice, which is actually MIG. So again, I write density of ice equals to mass of ice divided by volume, right? So let me put the relationship in. Density of ice times Vg. So this one gives me my second equation. Now, if you look at the ratio that I'm interested in up there, this ratio is actually U1 divided by U2. Okay, so I will take 1 divided by 2. So 1 divided by 2, so I have U1 divided by U2. Okay, U1 divided by U2 equals to density of water Vg over density of ice Vg. So I can cancel away Vg. So what I end up is I have density of water, which is 1.0 times 10 to the power minus 3 kilogram per cubic centimeter, and that for ice is 0.9 times 10 to the power minus 3. So that gives me a ratio 1.1. Now there's an extension question. What happens to the ratio if there were impurities in the ice? So if there's impurity, I would expect rho I to be higher than before. So if rho I is higher than before, the ratio will be smaller than before because density of ice is at the denominator. So I would expect this ratio to be less than 1.1. So the ratio will decrease. So if you want to see how I answer this, this is how I answer this. So with impurities, density of ice block increases, thus ratio decreases. Thank you.